Hi, physics. Mr. Janowski here. This is part 6 of the chapter 10 slides. In the last part, we talked about big spaceships in the future. We don't have these yet, that rotate around in order to create a sense of artificial gravity for their astronauts, and how that could actually work, but it would be problematic. You would need to make a very big spaceship in order to not make your astronauts perpetually nauseous. But yeah, it could actually work. So if you've seen that in a sci-fi movie, that makes sense. That would work. And we also saw some pilots training in a centrifuge to handle the big G forces that pilots, fighter pilots at least, have to undergo so that they avoid G lock. So if you didn't watch that video, go back and watch that. That's a short video, but very entertaining, so worth watching. So in this part, we're going to keep going with the stuff, and we're going to get back to ratio problems, which is everyone's favorite, I'm sure. And they're actually going to get a little bit harder. So I'll show you how to do a kind of trickier ratio problem. So let's get started. So first, this idea. What is an inertial frame of reference, and why do we like them so much? That is a frame of reference that is not accelerating. And we like them so much because if your frame of reference is not accelerating, you can do Newton's laws and they work perfectly well. And so do kinematics and conservation of momentum and conservation of energy, and all that stuff works very simply. If you want to try to do your physics in the other kind of frame of reference, a non-inertial frame of reference, meaning one that is accelerating, it can be done, but it's very, very tricky, and you're not going to learn how to do that kind of thing from me. You can save that stuff for like third year of being a physics major in college. So yeah, we like inertial frames of reference that are not accelerating. I mean, that's what they are by definition, because then we can do Newton's laws and everything works out great. The other question is, can an object have a constant speed and be accelerating at the same time? And the answer, of course, is yes, because speed and velocity are not the same thing. Acceleration is a change in velocity, and velocity is a vector. So velocity has magnitude, which is what speed is. Speed is the magnitude of velocity, and direction. So even if your object has a constant speed, if it's changing directions, then it is changing velocity. That means it's accelerating. So, for example, if you have an object moving with a constant speed in a circular path, it is in fact accelerating because its direction is always changing. So that's different than our everyday use of the word acceleration, but in physics, it definitely counts. If you're changing direction, you're accelerating. So speaking of that situation, we're going to have Alice and Billy both driving cars of equal masses around turns on level ground. So what provides the centripetal force to make this possible? So how are they able to turn their ground? How are they able to turn their ground? How are they able to turn their cars? They're able to do so because there is friction between their tires and the road. So that friction is what lets them apply a force. Well, actually, they apply a force to the ground. The ground applies a force back on them that makes the car turn. So you need that friction in order to turn your car. So if Alice were to move twice as fast, but Billy is turning twice as sharply, meaning his turning radius is half as much, how do their centripetal forces compare? So this is a ratio problem, and it's kind of an ugly one. So hang on tight. I'll show you how to do one of these. So here we are. Here's our problem. Let me get the red one out. Okay, so step what are we looking for? We are looking for how do their centripetal forces compare? That's not red enough for my liking. Let's go to this red. So step what we're looking for is the centripetal force of Alice over the centripetal force of Billy. We want to know what this is equal to, and what will its units be? Well, forces come in newtons, so the answer is obviously it's not newtons, because this is a force divided by a force. So something in newtons divided by something in newtons, the units will go away, and you're not going to have any units for this kind of thing. So F sub CA divided by F sub CB, what does that equal? That's what we're looking for. So when you get a ratio problem, the first thing you should do is make a list of all the things that you know. So we know that the cars have the same mass. So I'm going to start with that. Mass of Alice, meaning her car, equals mass of Billy's car. Alice is moving twice as fast. So let's see. How does velocity of Alice compare to velocity of Billy? VA equals space VB. Okay. I got the word twice here. So somebody's going twice as fast. The number is 2. Does the 2 go on the left or the right? Convince yourself that the 2 goes on the right. Because however fast Billy is moving, Alice's velocity is twice that number. So that's why that is. Now the next thing. But Billy is turning twice as sharply, meaning his turning radius is half as much. So how do radius of Alice and radius of Billy compare? So Billy's turning radius is half as much. So that means the half actually goes over here. Because whatever Alice's radius is, Billy's radius is 1/2 that number. So that's true, but let's do something right away. I don't like having a fraction here. So to get rid of this fraction, I'm going to multiply both sides by 2. So put a 2 over there and a 2 over there. So 2 times 1/2, well, that just cancels. And I'm going to end up with radius of Alice is equal to 2 times radius of Billy. So convince yourself that that's true. This is exactly the same to what I had earlier, but I don't like that fraction, so I multiplied everything by 2 to get rid of it. So you have that. And one more thing to write in is our formula for centripetal force. So the most important thing you learn in physics all year is F equals ma. In this case, force centripetal equals mass times acceleration centripetal. So let's change that up to this. V tangential squared, but I'm leaving off the tangential. So mass times V squared over R. So that's the formula we're going to end up using. So back to the idea we're starting with. We want to know F sub CA over F sub CB. So this is equal to something over something. Make the top something equal to the top thing and the bottom something equal to the bottom thing. So F sub CA, keep in mind this formula down here. So I'm going to write this. Mass of Alice, V of Alice squared over R of Alice. And on the bottom, F sub CB, well, same thing, but with B's. Mass of Billy times velocity of Billy squared over radius of Billy. So what I've just written here, this is true. However, it's ugly. I have a fraction in the numerator and I have a fraction in the denominator. I think this is called an improper fraction. Anyhow, it's terrible. I don't like it, so I have to do something about it. So let me do it this way. So it should be pretty clear that the mass of Alice, that belongs on the top, and mass of Billy, that belongs on the bottom. Those guys are staying in place. Maybe a little bit less obvious is that velocity of Alice squared, well, that's also definitely on the top. And velocity of Billy squared is on the bottom. And what are we left with? On the top, we have 1 over radius of Alice, and on the bottom, we have 1 over radius of Billy. So this is the tricky part. This is the ugly thing we're going to have to deal with. So let me rewrite this again, and then I'll explain what's going on with that bottom bit. So yeah, mass of Alice, that's cool. Velocity of Alice squared. Mass of Billy, velocity of Billy squared. All right, now we have to deal with this ugliness here. The 1 over RA divided by the 1 over RB. There's different ways of doing this. Mrs. Evans has a keep, flip, switch way, I think is what she calls it, a way to think about this. You can do cross multiplication is another way of thinking of this. You can multiply, the whole thing by RA over RA and RB over RB and see what cancels. You can do all kinds of things. When I get this kind of thing, I don't even think of the math. I do this purely rote, meaning a long time ago they told me how to do this, and I just remember the pattern of where everything goes. So I just move things according to the pattern. So I will explain it to you now. It's going to sound confusing, but this is honestly how I think of it. So radius of Alice. Well, that's on the bottom on the top, so therefore it must go on the top on the bottom. So that guy goes down to there. Radius of Billy. Well, that's on the bottom of the bottom, so it must go on the top of the top. And I'm done. Weird, but that is how I think of it. So find some way of doing the algebra that makes sense. So that's what we've got. So let's go back down to here. I'm going to rewrite this because I'm going to need a little bit more room. Force centripetal of Alice over force centripetal of Billy is equal to mass of Alice, v of Alice squared, radius of Billy, and in the denominator, and perhaps surprisingly, that should be an R, almost an R, radius of Alice. That doesn't look enough like an A compared to a B. Yeah. So MA, VA squared, RB on the top, MB, VB squared, RA on the bottom. So it looks weird, but that's how it goes. So now we have to go through and figure out what to keep and what to replace. Well, first of all, let me do something simple. Mass of Alice equals mass of Billy. So these guys do actually just cancel. I'm not going to go through the whole step with these guys. They just cancel. Those are actually the same thing in this case. If they had different masses of cars, that would not be the same, but in this case, they do have the same mass of cars. So now we get to VA, and that gets squared. So we're going to just go through term by term and either keep things or replace things. So do we want to keep or replace VA? Well, look at what we have right here. VA is equal to 2VB. So VA is very easy to replace. So I'm going to replace it with 2VB. And remember, because VA is getting squared, I've got to do this. VA was squared, so when I replace it with something, the whole thing I replace it with has to get squared. So I need those parentheses. And then we get to RB. Do I want to keep RB or replace it? Well, let's look at this guy right here. RA equals 2RB. Well, this 2 would make it a little difficult to replace it, so I'm going to keep RB. And I'll end up replacing the other one. So we've got that. Now we go to the bottom. So VB squared, keep it or replace it? Well, keep it. For two reasons. One is that 2, this 2, would make it difficult to replace. And the other thing is, I remember I already did the top. And the top is now in VBs. So I definitely want the bottom in VBs. So we get to RA. Do we keep it or replace it? Well, RA is very easy to replace, so we will replace it. So RA is becoming 2RB. And does anything cancel at this point? Yes. RB and RB cancels. I've got to keep the 2, and I can't cancel any of these things yet. You can't cancel the squares because that's not how algebra works. But I can get rid of the RBs. So now, because of PEMDAS, I'll do this. So 2VB quantity squared gives me 2 squared, which is 4 VB squared on the top. And on the bottom, I have VB squared times 2. That 2 is still there. So does anything cancel? Yeah. VB squared and VB squared cancels now. And that just gives me 4 over 2. So this better not be calculator time. 4 over 2 is 2. So what do we figure out? Centripetal force of Alice over centripetal force of Billy is equal to 2. So that's your answer. So the ratio of Alice's centripetal force to Billy's centripetal force is 2. The other way you can write this, equally correct, is you multiply both sides by force centripetal of Billy to get rid of this fraction part over here. And that would give you force centripetal of Alice is equal to 2 times force centripetal of Billy. Just a different way of thinking about it that for some people might be clear. What that means is Alice needs twice the centripetal force of Billy to do this. So back to the slides. If this is confusing, pause it here, go through this, try to remember. But I'm going back to the slides. So in this slide, I did all that stuff there. We got there. I'm not going to explain this because I just did. So basically what this means is Alice needs to get twice as much friction from the road to turn this quickly at her radius. So here's our expression for F sub c, centripetal force. If you want to turn twice as sharply, meaning with half the radius, how much more force do you need from friction? So if this number were half, that means this number is going to end up being twice as much, because a half in the denominator would end up being is the same thing as multiplying it by 2. Now, if you wanted to turn with twice the velocity, how much more force would you need? Well, look back at this expression. If I double v, what's going to happen to this? Does centripetal force double? No, it actually goes up by double squared. It goes up by a factor of 4. Because if v gets doubled and that whole thing gets squared, then I have 2 times 2 times v squared. So yeah, you need 4 times the force of friction. So yeah, many of you are learning how to drive now or have just learned how to drive. There's an important idea here. If you want to turn in a very sharp radius, yeah, you need more friction to do that. So you don't want to do that too much. But if you want to turn in the same radius, but you want to go twice as fast, you actually need 4 times as much friction. So when you're going around a turn, go slowly, because if you're going fast, you're asking for a whole lot of centripetal force to be provided from the friction between your tires and the road. And that's how you can get into trouble, by driving too quickly and making a turn. Going fast in a straight line, not that tricky, as long as you can be sure that you'll only be going in a straight line. Going fast around a turn, very tricky. It's harder. Going twice as fast and turning is actually 4 times as hard. So yeah, be careful. So I'll put links to these videos again because I like these videos. I'm sorry, I like this video. And the rotational motion Kahoot. So if you can, work out some way with some other buddy you have that's taking physics to try to do this Kahoot together, or at least, play the game yourself. Make sure you're good at the symbols and the units, because people love to make silly mistakes on these and they get really confused. So it's worth trying to do that Kahoot by yourself. And that's it for the slides. So hopefully you guys found that helpful.